Welcome to Unit 3, Lesson 5, Rates of Chemical Reactions. This is Mrs. Burt. By the end of this mastery session, you should be able to take the Unit 3, Lesson 5 assessment and master it. If you do not, give me a call, send me a K-mail, and we'll meet in a one-on-one session and go over the content together. So, Lesson 5 is all about chemical reaction rates. So we are talking about the rate at which a reaction takes place. For example, how fast does a chemical reaction actually take place? Is that something that we know? Can we time it? Is it a second, a minute, an hour? Can we speed up or slow down that reaction? The rate of a chemical reaction depends on several factors, such as temperature and concentration. Also, the use of a catalyst. So, if a catalyst is present, that catalyst may change the energy needed for a reaction to occur. Let's look at the reaction magnesium and hydrochloric acid. When you put magnesium into a hydrochloric acid solution, this reaction occurs. The symbols after mean, the S means it's a solid, the L means it's a liquid. This AQ means aqueous, which means it's in a water solution. And then of course the G means gas. So we have magnesium in the form of a solid, we have hydrochloric acid in the form of a liquid. Those reactants produce magnesium chloride, which is an aqueous solution, and hydrogen gas. So one thing, if we're talking about chemical reaction rates, what we want to know about this chemical reaction is how fast did the reaction happen? Did it happen in a second, a fraction of a second? All chemical reactions are not instantaneous, even if it seems that way. Even a huge explosion takes place over time. So all chemical reactions are processes that take place during a period of time. So that is the reaction rate, and the reaction rate is the speed of a reaction under specific conditions, because if you change the conditions, the rate of the reaction is going to change. So you determine the reaction rate by figuring out how much of the reactant is used up over a period of time, or how much time it takes place, or how much time it takes to form a certain amount of the product. And that is something that we can determine. You can see when we're looking at this graph, you can see the reaction marked with a blue line. So you have two reactions here. One reaction is marked with the blue line. One reaction is marked with the red line. When you're going up, that means total amount of product going across, time from start of reaction. So here is 0. So that's the beginning of the reaction. You can see that the blue line is steeper. Alright? The blue line became horizontal before the red line, indicating that this reaction happened faster than this red line. The graph above summarizes the differences in the rate of reaction at different temperatures, concentrations, and size of pieces. The steeper the line, the greater the rate of reaction. Reactions are usually fastest at the beginning. That does not change whether we use a catalyst or not. Reactions are usually fastest at the beginning when the concentration of reactants is greatest. When the line becomes horizontal, the reaction has stopped. So we want to know why this blue line reaction happened faster than this red line of reaction. And that is because we have changed some of the factors within that reaction. So what changed? The blue line had a higher temperature, had a higher concentration of reactants, and smaller pieces. Alright, so then the red line, we take a look at that one, it had a lower temperature, lower concentration of reactants, and larger pieces. So that changed the reaction rate of those two chemical reactions. There are several factors that determine the rate of reaction. One is temperature. So we just determined in that previous graph that that blue line had a higher temperature, so it was a faster reaction rate. So temperature definitely determines the rate of reaction. Also concentration. The more concentrated the reactants, the faster the reaction rate. Surface area. When the reaction involves solids, an increased surface area will result in an increased reaction rate. In this reaction, that had smaller pieces, which increased the surface area of those pieces. And lastly, a catalyst. The presence of a catalyst speeds up the reaction rate. So let's look at a catalyst. So it is an added substance that speeds up the reaction, but is not used up by the reaction. So speeds it up, but it's not used up by the reaction. It doesn't change that. A catalyst works by lowering the activation energy. So now we're adding something else into this, lowering the activation energy. And that is the energy needed to activate or start the reaction, which allows it to happen more quickly. Let's look at two chemical reactions. This is the same chemical reaction, but we're changing some of the factors, okay? We're changing some of these factors. So the blue line is an uncatalyzed reaction. So we're using the same reactants, we're getting the same exact product, except in one of these chemical reactions we have added a catalyst. The blue line represents an uncatalyzed reaction. You can see that it took longer to reach that activation energy for the uncatalyzed reaction. When you add the catalyst, represented in that red-purple color, the activation energy happens quicker. All right? The last thing that we want to add to chemical reaction rates is the idea of equilibrium. So far in all of the reactions we have looked at, we have made the assumption that reactants react to form products, and then that's the end of it. However, this doesn't always happen. A more accurate way to describe this kind of reaction is this way. You can see AB plus C, and then instead of having a single arrow pointing to the right, it is a double arrow. So we get AC plus B. Written this way, you can see the reaction occurs in both directions, and that's the idea of equilibrium. When a reaction, it's in both directions, forward and reverse. So when a reaction is finished, we say that the products and reactants have reached equilibrium. When we look at two graphs, so this gives us the visual. We get in this picture we got the words of what equilibrium, and now we're going to be able to see it in a graph form and kind of visualize what that looks like. So the top graph is rate versus time. The bottom graph is the amount of reactants and products versus time for an equilibrium. So you can see the red line is describing or showing us the forward rate of reaction. That would be this part here, AB plus C. That's the forward rate of reaction. You can see that at this point they have equal rates. So whether it is the forward rate of reaction or the reverse rate of reaction, they both reach equal rates. Let's look at amount versus time. So the amount of reactants decreases over time. The amount of products increases over time. Does the overall amount change? No. When it's at equilibrium, no change in amounts. So it's kind of going back to that idea of no energy, no energy lost or gained, it just changes. It's kind of the same idea for an equilibrium reaction. Hopefully, now that you have had a quick overview of Unit 3, Lesson 5, Rates of Chemical Reactions, you should be able to log back into the online school, take that assessment, and hopefully master that assessment. If you do not master it, please contact me and we can meet in a one-on-one session. Look over what you got wrong, go over those ideas, and get you to that mastery level. Good luck.